All right, so at the end of last class, we went through kind of a long derivation of what stress is. And one thing I didn't mention at the end of deriving it is that the stress tensor that we use in this class, and we mostly use, is actually specifically called the Cauchy stress. There are other stress tensors actually, and that's really the topic of graduate courses. But for the Cauchy stress, we can show, and we won't do it formally because it takes a lot of work and it's not really necessary. We can show that for the Cauchy stress, due to conservation of angular momentum, that the off-diagonal components are symmetric. And so we can actually reduce it such that there are only six unique components. Okay, so S12 equals S21, S13 equals S31, S32 equals S23. Okay. Again, this is due to the principle of conservation of angular momentum. And that's the reason it's symmetric. Okay. So we also showed or learned that the Cauchy stress, or stress, is really dependent upon your choice of coordinate system, right? And it turns out that there is a very particular choice of coordinate system that will diagonalize the stress tensor. And what that means is that in that coordinate system, there are no shear stresses. So there are no off diagonal. So the only stresses will be normal, right? So if we go back to our little hypothetical infinitesimally small cube, right, the only stresses will be normal. There'll be no shear stresses in this particular choice of coordinate system. Well, it turns out that that particular choice of coordinate system is called the principal directions, okay? And those principal directions are the eigenvalues of the stress tensor. And what's left when you use those eigenvalues to diagonalize the stress tensor, what's left, this S prime, is the principal stresses. Okay? So this equation should look familiar because I mentioned it when we talked about eigenvalue in the context of very basic kind of linear algebra concepts. But we didn't actually solve an eigenvalue problem, right? I said we'd hold off and do that in the context of stress. So that's what we're about to do. I did want to point out one thing. I think when I wrote this previously, I had written that this is Q transpose SQ, right? And now you see that I've changed that to Q inverse, where Q is a matrix of the eigenvectors, right? Well, the Q transpose that I had written before is not wrong, but it's only true if Q is so-called unitary. And what that means is that the eigenvectors are actually unit vectors, okay? So if Q is unitary, another word would be orthonormal. So that would be where Q is made up in the context of a 3x3 matrix, or the stress tensor, of the first eigenvector, second eigenvector, third eigenvector, where these guys are now unit vectors. So we basically, how do you turn a vector into a unit vector? You divide by its magnitude, right? So a unit vector, V1 hat, would be equal to the vector v1 divided by its magnitude. Okay. If you use MATLAB, if you use the eigenvalue function in MATLAB, the eigenvector matrix that it returns is unitary. It is made up of the unit vectors, okay, automatically. All right? Exactly. So for that was the point, right? The point is, for a unitary matrix, Q inverse is equal to Q transpose, which makes something nice about that, right? Finding the inverse of a matrix is typically a difficult process. If all I have to do is transpose it, that's not so difficult. So it's a nice feature. So again, if we diagonalize it, S prime will look like this, where I have now used S1, S2, and S3. And typically we order them in order from largest to smallest. So S1 is greater than S2 is greater than S3. That's typically how we order it. And again, Q is made up of the corresponding eigenvectors. Okay, so in this case, V1 is the eigenvector corresponding to S1, V2 is the eigenvector corresponding to S2, V3 is the eigenvector corresponding to S3. All right. Okay, so we'll work an example. So we're going to solve for the eigenvalues and eigenvectors of this matrix. And we're going to use some of those tools we learned in linear algebra, namely this idea of, well, the determinant initially, and then this row operations manipulation thing. Okay, so how do I solve for the eigenvector? How do I solve for the eigenvalues of S? Keep in mind that we're also solving for the principal stresses of S. Characteristic equation. We have to come up with the characteristic equation. How do we do that? Yeah, so it's we want to solve the determinant of S minus lambda I equal to 0 for lambda. Okay? So the first thing we'll do is write down S minus lambda I. All right? And that is equal to one minus lambda, 0, 0, 0, 3 minus lambda, minus 1, 0, minus 1, 3 minus lambda. Okay? Now we have to take the determinant of this guy. All right, so now we're going to take the determinant of this thing, and that's going to be equal to 0. So what's the determinant of that matrix? You remember I said the kind of the trick for solving the determinant is we take this guy and multiply by the determinant of this. So it's easier, we don't have to remember that long formula, right? And then we would take this and multiply by the determinant of this, right? And then this multiplied by the determinant of that. Well, it turns out we're lucky here, right? Because we have 0 multiplying something and 0 multiplying something. So we really only are concerned with what's in red there, right? So let's write it down. So we take 1 minus lambda times the determinant of 3 minus lambda minus 1, minus 1, 3 minus lambda. Okay. So that is equal to 1 minus lambda, 3 minus lambda squared minus 1. And so then we can factor that into 1 minus lambda minus 4, lambda minus 2. That's equal to 0. So what are the eigenvalues? Huh? 4, 2, and 1. In that order, right? We typically want to order them. So when we're talking about principal stresses, right? So we'll say that, S1 equals lambda 1 equals 4. S2 equals lambda 2 equals 2. And S3 equals lambda 3 equals 1. Everybody got that? Oops. Okay. So now we need to solve for so those are the eigenvalues. Now we need to solve for the eigenvectors. And if you remember, an eigenvector is a vector v that satisfies this equation. Okay? Where lambda is one of the eigenvalues. Right? So we need to plug an eigenvalue in, solve this equation, and we can solve, for v, and that'll give us an eigenvector corresponding to that eigenvalue. And, once I plug in a value for lambda, this is nothing but just a matrix. So something like AV equals to 0. All right. This is actually a vector, 0 vector. So we know how to solve this using our row operations, right? We solved last time we worked through a problem like this, it was AX equal to B, right? B had values, but now the values are just 0, and we use the row operations to solve for it. So that's what we're going to do. All right. So this matrix, what I've written A here, right, is 1 minus lambda 0, 0, 0, 3 minus lambda minus 1, 0 minus 1, 3 minus lambda. Okay, so for lambda equal to 4, then we have this problem. Minus 3, 0, 0, 0, minus 1. So, right, 3 minus 4, yeah, minus 1. Minus 1, 0, minus 1, minus 1. Now, I put the zeros over there just to be consistent with what we did before, but you don't have to, because understand, when we start doing row operations, we're adding and multiplying rows. We're multiplying rows by some value and adding them to one another. Well, there's always going to be zeros, nothing but zeros on the end right there, so I can just drop them because they're always going to be zeros. Right? Okay, so let's do our row operations, right? We want to try to get the thing into this, I don't know if I gave it a name last time, but that's called row echelon form or reduced row echelon form, where I'm trying to make this look like the identity matrix, right? So you'll notice that the second and third rows are identical. This will actually be characteristic of an eigenvalue problem. Okay, you'll always see this. So if I just multiply the second row by minus 1 and add it to the third, right, that eliminates the third row. So I can just say row minus row 2 minus row 2 plus row 3, right? And I'll write the result over here. I have minus 3, 0, 0, 0, minus 1, minus 1, 0, 0, 0. Okay, so I've dropped the zeros on the far right side. And then I can just divide the first row by 3 or minus 3, or however you want to do it. So yeah, you have 1, 0, 0. I'm also going to divide the second row by minus 1, 0, 1, 0, 0, 0, 0. Oh, this is a 1. Okay, so it's a little different than what we had before, where we just had a unique solution we could read off, right? We have to think about what this means. So I have a row of all zeros. Does anybody know what that means? Well, an eigenvector is in the null space of the matrix A. But what it means here is that there are infinite many solutions. Okay? So remember, what we're solving for here is a direction. Okay? And as long as I have the direction right, so I'm solving for a vector that's in a direction. Okay? As long as I have the direction right, no matter the magnitude of the vector, I will diagonalize the matrix, or it'll have a corresponding eigenvalue. Okay? So there are infinitely many solutions to this problem. And so to pick one that we can use, what we'll do is we'll sort of write down what this means, right? So what this means is, if you write down the equations, it means that V1, or the first component of V, which I'll use X, right? So X1, so this is, reading off this equation, that's X1 equals 0, right? It's X2 is equal to minus X3, and X3 is what I'll say is free. Means it could be anything, okay? So let's pick something. You could pick anything you want, right? Let's pick something. So I'm going to choose it to be equal to 1, okay? So then if I now have x3 equal to 1, I plug that in there. I have x2 equal to minus 1, and x1 is 0. So v1, or the eigenvector corresponding to the eigenvalue lambda equal to 4, is 0, minus 1, 1. Okay? Okay, let's look at this matrix. I probably skipped a step, but let's take a look at that. If I write this out, remember this is AV equals to 0. This is A. Okay, so let's write out the equations, right? So it would be 1x1 plus 0x2 plus 0x3 equals to 0. All right, 0x1 plus 1x2 plus 1x3 equals to 0. And then the last row is all zeros. You understand? Right. So then I just, now you just read off the answer, right? This doesn't exist, this doesn't exist, so it's just x1 equal to 0. And then x2 plus x3 equals to 0, which is the same thing as x2 minus x3. And x3 can be anything. Okay? So again, we may choose to make this a normal vector so we could compare our answer with, say, MATLAB, right? And if we do that, then we want to divide these by the magnitude. So the magnitude would be the square root of minus 1 squared plus 1 squared, right? Or 2. Right? So the square root of 2. All right. So I only write that down just to show that this is what you'd get if you looked up the answer in MATLAB. So that's just a unit vector. Okay? But any scalar multiple of that vector, right, because that defines the direction, any scalar multiple of that vector will correspond to that will be an eigenvector corresponding to that eigenvalue. You can choose it to be anything. You can choose it to be 144, right? It doesn't matter. Because when you compute, and that's why it's useful to put it in the unitary form, because when you compute the unit vector, it'll always be the same, right? No matter what I choose the magnitude, when I compute the unit vector, I'm going to get the same answer. Because it's just a direction. Remember? And remember physically what this is. It's a direction, right? What we're solving for physically is the direction, or the directions, the coordinate directions of stress in which there are no shear stresses. Okay? And this will have a valuable meaning to us as far as the Earth and geomechanics really shortly. Okay? So, you guys want to work out the second one, or is that okay? I mean, we can work through the details to solve for the second eigenvalue. Let's just do one more, and then the third one I'll just give you the answer. Okay? Yeah. We'll get to it. Yeah, it's like the next few slides. We'll get to it today. Okay, so sorry. So for lambda equal to 2, right, that's our second eigenvector. So for lambda equal to 2, we have minus 1, 0, 0, 0, 1, minus 1, 0, minus 1, 1. This is the equation we're solving. So what should we do? Maybe just add the second row to the third? Minus 1, 0, 0, 0, 1, minus 1, 0, 0, 0. All right, so this is x1 is equal to 1. I'm sorry, x1 is equal to 0. x2 equal to x3. x3 is anything. I'm going to choose it to be 1. Okay, so then I have v2 is equal to 0, 1, 1. All right. Or in terms of the unit vector, 0, 1, 1. All right. I'm sorry? Oh, so again, I'm trying to get the matrix in that so-called reduced row echelon form, or where this looks like the identity matrix. Okay? Now, I can't get there because of the nature of the matrix. So I do as many operations as I can to try to get it in that state, but unfortunately, when I get it to this, that's all I can do, right? I can't, there's nothing to add to help me eliminate that minus 1 there, right? Yeah. Well, also just by looking at them, I can see that they're not linear independent, right? They're just multiples of one another. That's what I mean when I say linear independent. They're just multiples of one another, right? Just multiply minus 1 times the second row, and I can get the third row, okay? These are characteristics. An eigenvalue problem will always be like that. So if you're trying to solve for an eigenvector and you don't get a scenario where you have at least one linear, one row of zeros, you did something wrong, right? Eigenvectors are never, the solution is never unique. There's always infinitely many solutions, right? Because really all we're interested in is the direction, not the magnitude. Okay? So I think I'll forego going through the process for the third one because it's just the same. And, the results are just like this, right? So we worked out for the first two, right? This was our V1. This is what we got for V2. V3 would have been like this. Okay? So let's try something. Okay. All right, let's try something. So my favorite programming language is Python. Okay. I can program in about 10 different languages, but my favorite one is Python. And I'm not going to preach to you, but once you learn Python, you'll never use MATLAB again. They're very similar in some respects, but Python can do a lot more. So what I'm going to do is I'm going to define this S matrix, our stress matrix. So it was 1, 0, 0. 0, 3, minus 1. Can you guys see that? It might be a little hard, but you'll certainly be able to see it in the recording if you go back later. 0, minus 1, 3. Okay, so I should be able to then do NP, linalg, eig, vals, S. Okay, so I solve for the eigenvalues of S. I think if I do NP linalg eig, if I just do eig, it should give me the eigenvectors as well. So it actually gave me the eigenvectors and the values. So vals vex equals, and let's look at the vex. Oop. So those are the eigenvectors, and you should see, if you know what 1 over the square root of 2 is, you know it's like 707, right? So that's exactly what we got. Okay. So just also, let's say, well, to use the notation that's consistent with I've been using, let's call my values we'll call it SS, okay, and then we'll call this Q, or we'll call this S prime, SP for S prime, and Q is my vectors. Okay, so let's see what happens if I take Q, and we know it's unitary, so we can just take its transpose. I'm going to take the dot product of S with Q, and then the result of that, I'm going to take the dot product of Q transpose. See what we got? That's S prime, right? Here SP is just a, but if we put those on the diagonal, right, that's what we got. So it works. Right? The eigenvectors, or the principal directions of stress, will diagonalize the stress tensor. Okay. Now we'll go on to see why